So good evening to one and all. Is the AV clear to all? Yeah. Thank you. Is that clear? Audio and video to everyone? Say. Right. So let us start our today's session. So before going to start, do you have any questions for the previous session? What we discussed? So thanks to all. And I wish the same for to you also, whoever are the teachers today in the class. Yeah. So n factorial by n plus 1 whole power n into x power n. This was the question, right? Yeah. So first of all, tell me what method you have approached here to verify the convergence. Ratio test. That is right. So let us go with it again. So this is un equal to. So if you take un plus 1 equals to n plus 1 factorial by n plus 2 whole power n plus 1 into x power n plus 1. So if you consider the ratio un by un plus 1 equals to n factorial by n plus 1 whole power n into x power n into n plus 2 whole power n plus 1 by n plus 1 factorial into x power n into x. So however x power n gets cancelled and n factorial gets cancelled. Here you have n plus 1 whole power n. So you can write it as n plus 2 whole power n plus 1 by n plus 1 whole power n plus 1 into 1 by x. Am I correct here? Right. So you can write it as so taking n gets cancelled here. So if you apply the limit, it will be 1 by x. And here you have e 1 by ex. Am I correct? The limit part. Did you get the same one or you have a different one? Please tell. Do you have the same limit part 1 by ex? So if you say this is 1 plus 2 by n whole power n, even though if you apply limit, this part will be 0, isn't it? So that's why this will be 1, this will be e, again 1, and this will be 1. So 1 by ex, I got like that. Do you agree for the limit portion? Right? So if I say, so if you apply limit, how do we take? This will be 1, isn't it? Or you have a different value? Right? So When 1 by x is greater than 1, it is convergent, less than 1 divergent, equal to 1 test phase. When equal to 1, you take the other case. When x equal to 1 by e, you take the other case. When x equal to 1 by e, right? Is that sufficient for you in getting the logic? Fine, thank you. So any more doubts for anyone? So 1 by log n whole power p. Yeah. For this, first tell me what approach we have followed there. Or what test we have applied there on seeing the term. Or you don't have any other idea. You just take the case of Cauchy's condensation test. So you take that un is equal to 1 by log n whole power p. So, or you can take it as f of n is equal to. So you take a power n into f of a power n, right? So this is equal to a power n into 1 by log a power n whole power p. This equals to a power n into 1 by n log a whole power p equals to can you write like that the value? So if you are able to decide what we can say about that series. Suppose if you are not interested under Cauchy's condensation test, we should go for the other one, right? Suppose so this is, suppose if you are applying for ratio test, let me say. So can you find the integration for 1 by log x whole power p? Is that possible? Do you have any formula for finding integral 1 by log x whole power p? Please tell. Any guesses? Say. Any guesses for anyone? Is there any formula to find 1 by log x whole power p? So limit value is 1 by a. So if you have applied ratio test, you are saying that, or for this one, a power n into f of a power n. Yes, for condensation, right? So you take un is equal to and u n plus 1 is equal to a power n plus 1 by log a whole power p into 1 by n plus 1 whole power p. So if you calculate un by un plus 1, a power n by log a whole power p into 1 by n power p into log a whole power p into n plus 1 whole power p by a power n plus 1. So a power n, this thing gets cancelled, log a whole power p gets cancelled, and this is equal to, taking n as common, n power p into 1 plus 1 by n whole power p by n power p into a. So this is equal to 1 plus 1 by n whole power p into 1 by a. Therefore, limit un by un plus 1 is equal to limit of this value, this is equal to 1 by a. Is it visible to all? The top part, what I have written there, that part is not visible for you. So I have simply calculated un by un plus 1. You please check on that. The last part will come like that, otherwise I will write again. So up to this you are clear, right? Up to this part. So the methodology what we are applying here to test the convergence of the series, is it clear for you, or you want the beginning again? So here we are applying the Cauchy's condensation test, right? So we take the given function as f of n. To apply Cauchy's condensation test, you need to take the series of the form a power n into f of a power n, where a is greater than 1. Any number you can take, 2, 3, 4, 5 you can take. So this is the form. So, and if you are able to say that this series is convergent, then given series is also convergent. That's why this part I am taking it as un, and un plus 1 will be like this. I am calculating un by un plus 1. Fine. So if you are not clear with the top part, I will write it again. If you have done un by un plus 1, this equals to a power n by log a whole power p into 1 by n power p into log a whole power p into n plus 1 whole power p by a power n plus 1. So log a whole power p gets cancelled, a power n gets cancelled, a will remain here. Again you have, taking n common here, 1 plus 1 by n whole power p by n power p gets cancelled here, it will be a. Is that okay now? un by un plus 1 value. So if you apply limit here, limit n tends to infinity un by un plus 1, it is nothing but 1 by a. So please understand, what is the criteria for a? You can take a as any number, 2, 3, 4, 5, so on. So if you take a is equal to 2, it will be 1 by 2. The value is less than 1, isn't it? Therefore, by ratio test, it is divergent. You can take a as any number which is greater than 1. You can take a is equal to 2, 3, 4, 5, 6, any number you can take. So the solution for it is, since this series is divergent by ratio test, the given series 1 by log n whole power p is also divergent. That was the conclusion. Okay. Is it okay for you? Any more clarity you need? Thank you. So let us start our today's session. So this session will complete the concept of infinite series. So in the next session, we are going to discuss about limits and continuity. That will be somewhat interesting for you. The objective of today's session will be, we are talking about the alternating series, and in which case we consider a one test which is called as Leibniz test. Later, I move to the concept of absolute convergence, and followed by conditional convergence. So this is the concept of today's session. Fine. So please take a note of it. So earlier we have discussed what is meant by an alternating series. So whenever you have written a series whose terms are alternatively coming, this kind of series we call it as the alternating series. One plus 2 by n whole power n equal to e square. This is e. So how do you deduct that this value is equal to e square? Let me say this part is nothing but do you accept for n times? However, I will discuss this part again separately. Okay, let me finish the class session because we are deviating. Right. So coming to alternating series, whenever you have written a series of this form, we are calling it as alternating series, whose terms are coming with alternative signs, and you are checking its convergence, the sum of all these terms you are taking. Summation n is equal to 1 to infinity minus 1 whole power n minus 1. You can take un or an, whatever the series it is. You can take the other notation as summation n is equal to 1 to infinity minus 1 whole power n plus 1 un. This also you can write, because usually first term will be positive, then negative, etc., etc. That is going to come. And the statement of Leibniz test is the sequence un, what you are taking is, it must be a decreasing sequence. And secondly, for the nth term un, if you apply limit, it must be equal to 0. If the two conditions are satisfied by the series which you have taken, then the alternating series is convergent. That is the statement of Leibniz test. Fine. Please take a note of that statement. The series which you have taken must be a decreasing sequence, and for the nth term, if you have applied limit, it must be tending to 0. Then the alternating series is convergent. Is that clear? Yes or no? Okay. So coming to the part of absolute convergence. So apart from taking this series, you consider modulus. That means for the alternating series, what you have taken, for the term here, you are putting the modulus. So what happens? All the values will become positive, isn't it? So if this value is convergent, then we say that the given series is absolutely convergent. So for absolute convergence, what we are doing? We are taking modulus for the terms un. And to verify its convergence, you can apply all the previous tests what you have learned, like comparison test, limit comparison test, ratio test, whatever it is. You can apply all the things to decide the convergence of modulus of un. And one result is that if the series is absolutely convergent, it implies our regular convergence. Okay. So if you put modulus for the terms, if it is convergent, then we are calling it as absolute convergence. And if the series is absolutely convergent, then by default it becomes convergent. There is no need to verify the convergence by removing the modulus. Fine. So, and the part of conditional convergence is nothing but if I consider un, it is convergent. If I consider modulus of un, it is divergent. To understand the difference, if you take the sequence as it is, it will be convergent. If you put the modulus, it will become divergent. So if this type of situation arises, then we say that the series is conditionally convergent. Okay. Is this clear to all? The definitions part? If everyone is clear with this, then let us take some problems. Fine. Now, let us take the problem that summation n is equal to 1 to infinity minus 1 whole power n plus 1 into 1 by n power p. This is the problem given. So first of all, I am taking the problems only on alternating series, not for the absolute convergence. Okay. I am taking the problems only for the alternating series. So what are the series given here? If you have written this, it will be 1 minus 1 by 2 power p plus 1 by 3 power p minus 1 by 4 power p plus so on. This is our given series. Now, if you take the nth term, un is equal to 1 by n power p. Please understand one thing, that if you are checking for regular convergence, the nth term un will be written by excluding the sign. If you are writing for absolute convergence, then you write mod un. In that case, we consider the sign also. So in that case, you take that modulus of minus 1 whole power n plus 1 into 1 by n power p. That we will write. So if you are considering for regular convergence, we exclude the sign. If you consider for absolute convergence, we include the sign. Fine. Is it clear for all? right? Now, whenever alternating series is there, the only test condition available is Leibniz test. So Leibniz test says that the sequence what you have taken must be decreasing, and if you apply the limit for the nth term, it must be equal to 0, then it becomes convergent. So first I must prove that it will be decreasing one. So if you take un plus 1, it will be 1 by n plus 1 whole power p. So I can write that since n is less than n plus 1, so n power p is less than n plus 1 whole power p. So 1 by n power p is greater than 1 by n plus 1 whole power p, which is nothing but un is greater than un plus 1. Agreed? Since un is greater than un plus 1, it is a decreasing sequence. Now we need to apply the limit. So limit n tends to infinity un you consider. So limit n tends to infinity 1 by n power p, it is nothing but 0. So by Leibniz test, it is convergent. And the statement you take p greater than 0 for all. So if p is 0 to 1 or p is equal to 1 or p is greater than 1, whatever the value you take, the alternating series is convergent. So are you getting the idea behind this problem? I just simply mentioned that p is greater than 0. So p will be any number. P is equal to 1, p is equal to 2, p is equal to 1 by 2, anything you can take. P must be a positive number. So if you consider the alternating series, it is convergent. So if I say that p is equal to 1 by 2, the series is nothing but 1 by root n. So it is also convergent. Now, if you want to test for absolute convergence, so you consider modulus of un. So this will be 1 by n power p. Because I am putting the modulus for this sign also. So sigma un, I mean sigma mod un, if you consider sigma 1 by n power p. So by p series test, p greater than 1, sigma mod un is convergent. If p less than or equal to 1, sigma mod un is divergent. Now see the difference. If you consider the alternating series, the series with plus minus symbols, then it is becoming convergent by means of Leibniz test, whatever the p value you take. But if you consider the modulus for the absolute convergence, by p series test, it is becoming convergent whenever p is bigger than 1, otherwise it is divergent. So if you are putting modulus, it is becoming divergent for some values of p. But if you remove modulus, it is becoming convergent. So here we say that the series is conditionally convergent, because whenever you are putting modulus, it is becoming divergent for some instances of p. Okay? Are you getting? In a nutshell, you can write like this. Now see, say the possibilities for p greater than 0 are 0 less than p less than 1, p is equal to 1, p is greater than 1. Accepted? Say. Right. So, if you take the alternating series, if p is lying between 0 and 1, is it convergent or not? It is convergent. If P is equal to 1 also, it is convergent. If P is greater than 1 also, it is convergent. How I am saying it is convergent? By means of Leibniz test, the alternating series is convergent for all values of P. And if you put modulus, when P is greater than 1, then only mod UN is becoming convergent. So it is convergent here, it is divergent here, it is divergent here. So this is the condition for UN, this is the condition for mod UN. Please check that. So does it make sense? If you take UN as it is with the sign itself, the alternating series, for all values of P, it is convergent by means of Leibniz test. If I consider mod UN, so if you want to write mod UN particularly, modulus of UN is equal to -1 whole power n minus 1 into 1 by n power P modulus. If you want to write it exactly, you should write like this. Since you are applying modulus, it is becoming positive. Since n is always a natural number, it is positive. So by removing modulus, straight away we write like this. Fine. So when P is greater than 1, UN, mod UN, both are convergent. So when P is greater than 1, it is absolutely convergent. For these cases, modulus is divergent, regular series is convergent. So for these two cases, we say that it is conditionally convergent. Is the concept clear now? Yes or no? Right. Can I take the other problem? Okay. Now take the case of summation is equal to 1 to infinity -1 whole power n plus 1 by log of n plus 1. So if you expand the series, it is nothing but log 2 minus log 3, say 1 by log 2, 1 by log 3. This is the series. So whenever a problem is asked for absolute convergence, then definitely we should apply modulus there and we should check for convergence. Please understand one thing, that if the problem is given that test the convergence of the series is given and you have an alternating series here. So what is the approach of the problem while doing? Since you have an alternating series, you can go for two approaches. One approach is applying the Leibniz test. Second approach is you consider mod UN. Means you are checking for the absolute convergence. Why I am checking for absolute convergence? Because absolute convergence always implies the regular convergence. So either of the approach you can follow. Now if the problem is particularly asked test the absolute convergence of, then always you should apply modulus first. Okay? Is the problem approach clear? Any questions, please? Fine. Can I continue then? Now, let us write the term here. It is just like I want to apply Leibniz test. So you take un is equal to log of n plus 1. So if you consider un plus 1, it will be log of n plus 2. Now what happens? You need to prove that it is a decreasing sequence. How I am going to prove that? As we have n plus 1 is less than n plus 2. Log of n plus 1 is less than log of n plus 2. So 1 by log of n plus 1 is greater than 1 by log of n plus 2. This is nothing but un is greater than un plus 1. So it is a decreasing sequence. And if you consider limit un, so limit n tends to infinity 1 by log of n plus 1. It is nothing but 0. Accepted? So it is satisfying the two conditions. Therefore, by Leibniz test, the alternating series is convergent. If you mention the word Leibniz test, it means that you are verifying the convergence of the alternating series, the series whose terms are having plus minus symbols. Okay? Any questions over this part, what I considered? So, if you want to check for absolute convergence, so if I write mod un, sigma mod un, you can write like this also, summation n is equal to 2 to infinity mod un, you can write. So this will be summation n is equal to 2 to infinity 1 by log n. Since I am applying modulus, all minus signs will become plus. In other words, you are checking the convergence of the series 1 by log 2 plus, 1 by log 3 plus, 1 by log 4 plus, so on. You are checking the convergence of this series whenever you put modulus. Right. Now, how to verify that this series is convergent or divergent? Is there any technique for us? So one identification is always log n series is divergent. Or since log n is there, you can apply the Cauchy's condensation test to verify its convergence. Or can you suggest any other test here to verify the convergence of 1 by log n? Anybody? Please tell. Any idea how to verify the convergence of this part? Yes or no? So, can you recollect any test which is applicable for 1 by log n to verify the convergence of it? or you are not getting any idea for it? Yes, you can apply Cauchy's integral. Apart from this, can you apply any? That is what I am asking. You can apply Cauchy's integral. So just apply Cauchy's integral and tell me whether it is convergent or divergent. The Cauchy's integral test or Cauchy's condensation test you can apply. The answer is it is divergent. Fine. Are you trying that? Yeah. So take your time. Yeah, that's right. 1 by a is the limit. Since a is greater than 1, the value is less than 1. Exactly. You can take a is equal to 2, 3, 4, anything you can take. So the value is less than 1. So by Cauchy's condensation test, what we can say? The series is divergent. Because you have applied the ratio test there, the limit value is 1 by a. Since 1 by a is less than 1, by ratio test, a power n into f of a power n is divergent. Therefore, f of n is divergent by condensation test. So this is by ratio test and this is by condensation test, nothing but 1 by log n. Right? So did you apply any other test? You have applied the same thing apart from ratio test. Okay. Now let us take one interesting question. It is also asked in the previous year papers. I hope so. You take the series summation n is equal to 1 to infinity minus 1 whole power n into cos n alpha by n root n, where alpha is a real number. This is the problem. So we need to verify absolute convergence, whatever it is. It is given that summation n is equal to 1 to infinity minus 1 whole power n cos n alpha whole divided by n root n, where alpha is a real number. Now the question answer is very simple. First of all, we go for the absolute convergence. So you straight away consider that sigma mod un. This is equal to, if you put modulus, this will be summation modulus of cos n alpha by n power 3 by 2. Accepted? As we know that modulus of cos x less than or equal to 1, you can say that this is less than or equal to summation 1 by n power 3 by 2. And since by P series test it is convergent, therefore by comparison test this is convergent. So it is convergent by P series test, it is convergent by comparison test. What does a comparison test gives? Whenever you have a series, you need to bring up a series which is bigger than this. If the bigger series is convergent, then smaller series will be convergent automatically. So you have proved that sigma mod un is convergent. It means that given series is absolutely convergent, since you have verified the convergence by putting modulus, and absolute convergence always implies the regular convergence, therefore it is regularly convergent. Here regularly convergence means the alternating series is convergent, that we need to understand. So apart from checking the Leibniz test for the alternating series, straight away you are putting modulus there. So you are verifying for the absolute convergence. If it is absolutely convergent, alternating series will be convergent trivially. And to get the absolute convergence, I am making use of the comparison test. Okay? Is the logic clear? Yes or no? So if you have any doubts, you can ask right now with regard to the approach. Anyone you can ask. Very good question. So you are saying that if I am verifying for absolute convergence, that means if I put modulus there, the result is giving it as divergent. Then what about the regular convergence? Is that your question? Yeah. So if you put modulus, if it is divergent, okay. So if you remove modulus, it is nothing but the alternating series, right? So you will apply the regular procedure of alternating series and verify its convergence by means of Leibniz test. So if it is convergent, so by putting modulus, you are getting the result as divergent. If you remove modulus, it may be converge or diverge. So in that case, we say that if it is convergent, alternating is convergent, modulus is divergent, we say it is conditionally convergent. If it is divergent here, in such case we say that sigma un is divergent and sigma mod un is also divergent. We write like that. Okay? Is that clear for you? The way of expression. Any other queries for anybody? With regard to absolute convergence and conditional convergence? Yes or no? Fine. Shall I proceed then? So this is the problem. So test the convergence of log of 2 by 1 minus log of 3 by 2 plus log of 4 by 3 and so on. Yes, if the given series is absolutely convergent, then there is no need to find a regular convergence. Right. So after discussing with this problem, I will draw a picture for you which gives a clear idea. Fine. That will give a good idea what we are doing for a problem. So please take a note of it. After noting, please inform. Right. So if you write the nth term, see it is an alternating series. I am not going for the absolute convergence since the question is given that test the convergence of. So I am not verifying absolute convergence. I am just verifying the regular convergence. So I need to make use of the Leibniz test. So you need to take u1 is equal to log of n plus 1 by n. Am I correct in writing the nth term? By n is equal to 1, 2, 3, so on. Right. So if you calculate the nth term limit, it will be limit n tends to infinity log of 1 plus 1 by n. Applying the limit, it will be log 1 equal to 0. Agreed? So among the two conditions, one condition is satisfied. What is the other part there? You need to prove that it is a decreasing sequence. So if you write un plus 1, it will be log of n plus 2 by n plus 1. Here the question comes, how can I prove that it is a decreasing sequence? My intention is I should show u1 is greater than un plus 1. So how I am going to show that? Any idea how to prove that it is decreasing? Any guess for anyone? Just imagine the case of monotone convergence theorem. If you want to prove that a series is monotonically increasing or decreasing, what we do? So one procedure is you take the difference un minus un plus 1. If you consider that, it must be greater than 0. That is one logic. Otherwise, if you are able to build a construction for the two things, then you can do. How you can? One logic is, I can say like this, n is less than n plus 1 and 1 by n is greater than 1 by n plus 1. By comparing the terms, you should bring a relation for them. So if you write that n plus 2 by n is greater than n plus 1 by n, are you able to build a construction here? With the terms u1 and u1 plus 1, it is okay. Otherwise, our regular procedure is simply consider the difference between them. Either u1 minus u1 plus 1 or u1 plus 1 minus u1. Whatever the case you can take. Yes, you can apply the case of derivative thing here. So if you consider u1 plus 1 minus un, it will be log of n plus 2 by n plus 1 minus log of n plus 1 by n. It will be log of log a minus log b Can I write like that? Is this correct expression? Say. Yes or no? So if you simplify that, right. Now here comes the case. If I prove that the value inside the part of logarithm is, say, less than 1, then I can say that whenever a value which is less than 1 under logarithm, log value will be negative, isn't it? If you consider log of 1 by 2, it will be negative. Say, whenever you take a value for logarithm, the value is lying between bigger than 0 and smaller than 1, its value will be negative. You know that or not? Log 1 is 0. If you take log 2, it will be positive. So if you take a value between 0 and 1, it will be negative. Say, you know that part or not? Right. So here what happens? This is n square plus 2n. You are dividing n square plus 2n with n square plus 2n plus 1. So denominator is bigger than the numerator. So what happens? This value will be obviously less than 1. Since this value is less than 1, log of this value is nothing but negative. This is nothing but less than 0. So you have proved that un plus 1 minus un is less than 0. It is nothing but un is greater than un plus 1. Therefore, it is a decreasing sequence. By Leibniz test, it is convergent. That is the conclusion. Any questions? Say. And let us take one problem. Can I erase this? Yeah. So earlier, while discussing the concept of absolute convergence and conditional convergence, I will draw the picture, then you will get a whole idea. This is the question tag. Test the convergence of an alternating series is given. Now the task before us is, what is the approach to verify its convergence? See, the question is asked only for that test the convergence of, not of absolute convergence. So here what I am saying, on observing the series pattern, if you are able to apply Leibniz test, always we should go with Leibniz test. If you feel that applying Leibniz test is somewhat difficult, then you verify for absolute convergence, because absolute convergence implies the convergence. You can follow either of the approach if the question is given for an alternating series in that pattern. Okay. Is that fine? Yes or no? Right. If the question tag is like this, test for absolute convergence, comma convergence. If this is the question tag part, since the word absolute is mentioned here, you should always start with mod un. Because the word is containing absolute convergence, the term. So, if it is convergent, then by default, it is convergent. Always alternating series is convergent. So when there is absolute convergence is satisfied, there is no need to verify the regular convergence. If at all it is divergent, means since you are putting modulus, it is becoming divergent. So you need to verify whether the regular convergence happens or not. How to? By applying Leibniz test. So if it is convergent, then we say that it is conditionally convergent. This is the whole idea. Okay? Right. Anybody has any other doubts with regard to the approach of a problem? What we have to do? So based on the question tag, we are doing an approach. Any other questions, please, for anyone? So can I take the other problem on this? Fine. So this is the problem. It is also earlier given. Prove that x minus x cube by 3 plus x power 5 by 5 plus so on is convergent if minus 1 less than or equal to x less than or equal to 1. After noting the question, you please inform. Now, as per the approach given earlier, you please give me the methodology what I have to follow now. Right. Leibniz, that is correct. Any other thing? Yeah. If you observe the pattern there, minus 1 less than or equal to x less than or equal to 1, you have to verify the convergence when x equal to minus 1, when x equal to 1, and minus 1 less than x less than 1, which is nothing but mod x less than 1. Isn't it? Do you agree or not? As per the range of the x is given that. So, if I put x is equal to 1, the case, the given series is nothing but 1 minus 1 by 3 plus 1 by 5 minus 1 by 7, so on. Accepted all? So if you write the nth term, un is equal to 1 by 2n minus 1. I am excluding the symbol. So for this, I am applying the Leibniz test because it is the alternating series. So you take un plus 1, that is equal to 1 by 2n plus 1. I can write that 2n minus 1 is less than 2n plus 1. So 1 by 2n minus 1 is greater than 1 by 2n plus 1. So un is greater than un plus 1. However, limit un is equal to 0. You accept or not? So by Leibniz test, it is convergent. So even though if you write x is equal to minus 1 in the given series, it is going to come as minus 1 plus 1 by 3 minus 1 by 5 plus 1 by 7, so on. So again it is convergent by Leibniz test. Because this series is nothing but minus of this series. Since it is convergent, this limit is nothing but minus of this. So if you want to apply, you can apply Leibniz test here. No problem at all. So if you put x equal to 1 or x equal to minus 1, by considering the Leibniz test, I can say that it is convergent. Any queries so far? If everyone is clear, I go to the next level. Shall I proceed then? Okay. Now, now the other case remains here is I am taking x as minus 1 less than x less than 1. You can take x is equal to 0.5 minus 0.5, 0.3 minus 0.3, anything you take. So x value is a parameter here. So to verify the convergence, apart from applying the Leibniz test here, I am applying the modulus here. So I am saying minus 1 is less than x less than 1. Because by applying modulus, if I am able to say that it is convergent, since it is absolutely convergent, alternating series will be convergent automatically. Clear? So there is no need to apply any other test separately. That's why, as and when the case is considered minus 1 less than x less than 1, I am considering mod un apart from taking Leibniz test. Okay. So mod un, if you consider, the form is mod x power 2n minus 1 by 2n minus 1. Because in the denominator you have 1, 3, 5 odd numbers. Power is varying as odd numbers. Since x value is not known to us, it is varying between these two. I am putting mod here. Is it clear how to write the mod un value here? So if you write mod un plus 1, so consider the ratio test. This equals to now how to simplify this? So you can say this is 2n minus 1, this is 2n plus 1. Here you get x square remains, and this will be 2n plus 1 by 2n minus 1. Since it is x square, even though if you remove modulus, it is always positive. So I remove modulus. So if I apply the limit here, it will be 1 by x square. So as per the ratio test is concerned, if 1 by x square is greater than 1, it is convergent. That is 1 is greater than x square, that is x square is less than 1, that is mod x is less than 1. And when 1 by x square is less than 1, it is divergent. That is mod x is greater than 1, it is divergent. So this is the whole idea. So this is one kind of previous year problem asked. So did you feel any confusion here in the approach so far discussed? Anyone? Please tell. Or if I go fast, you can ask. I will repeat the process again. Yeah. Why we are not keeping power in modulus? Means you are asking that mod 2 per n minus 1 you are asking. See, n is by default natural numbers, right? It is always positive there. Because if you write n, by default it is natural number. It starts from 1, 2, 3, 4, so on. It won't become negative at all. That's why I skipped that part. Right. Any other questions, please? Was that problem considered? Is everyone clear? Fine. So I just want to introduce one small concept here by taking a previous year problem. Then I will wind up our session, the discussion on infinite series as well as alternating series. So since the topic is completed, I am going to give a small assignment for you. By doing the assignment, you will have the clear idea on what we are doing actually. So if it is given that summation n cube plus 1 whole power 1 by 3 minus n by log n. This is my problem. Please understand, I am out of the concept of the alternating series now. I am not talking at all alternating series. I am talking about a series is given like this. We are just want to know whether it is convergent or divergent. That is our whole idea. Okay. Is that clear or not? So if you observe the nth term, if you want to apply ratio test or condensation test or Gauss test or whatever the thing is, are you able to feel that am I going to simplify this nth term by means of any methodology? If I apply ratio test or Rabi's test or integration test, whatever it is, the very first look gives an idea that it is very difficult, isn't it? N cube plus 3 whole power 1 by 3 minus n whole divided by log n. So the very idea it is, if you consider that this whole thing as a single series, you have a confusion. Let us feel that this is nothing but n cube plus 1 whole power 1 by 3 minus n into 1 by log n. It gives a small idea here. So that single series, we are feeling that it is the product of two series. One is 1 by log n, another one is this one. Will you agree? Right. So the main idea is, whenever the nth term looks like this, there is one interesting concept called as Abel's theorem. I don't want to give the illustration of the theorem. It simply says that if the given series is in the product form, say sigma an and un, there are two series. One series is an and one series is un. So among this, one must be a convergent one and one must be a decreasing one. So let us say an is monotonically decreasing and un is convergent. Then the product series will be convergent. This is called Abel's theorem. So if the given series is in the form of a product, then if you are able to view it as product of two series, among which one series is a convergent one, you are able to prove that, and the other one is monotonically decreasing one, then the result is the product series is a convergent one. So usually problems of this type won't come in the examination point of view. However, if the level is difficult, this kind of thing you can expect. So you can say this is 1 by log n, you take that this is an. Do you agree it is monotonically decreasing? Yes or no? Yeah. And if you take this is un, I need to specify that it is convergent. Yeah. How it is convergent? Earlier we have proved the same problem by doing a rationalization. The formula a cube minus b cube is equal to a minus b into a square plus 2ab plus b square by a square plus 2ab plus b square. Could you recollect that problem? We have done that problem earlier. Using the limit comparison test we have proved. So if one series is monotonically decreasing and one series is convergent, you must specify by means of any idea it is convergent. So whenever a problem is given in the form of a product series, you should prove two conditions. One, the series which you have taken is monotonically decreasing. You should prove that. Second, the series which you are saying that it is convergent, you should prove that it is convergent. Then by Abel's theorem, the result is convergent. Okay. I just want to introduce one small problem over this concept, then I will wind up the session, which gives a clear idea overview. Fine. Shall I erase this? So this is the problem. So 1 minus 1 by 4 into 3 plus 1 by 4 square into 5 minus 1 by 4 cube into 7, etc. Now please understand, if you write an nth term for it, we can write the nth term. So since the symbols are varying as plus or minus, etc., and here the powers are varying as 4 power 1, 4 square, 4 cube, etc., and we have the odd numbers 1, 3, 5, 7, so on. You can write it as summation n is equal to 1 to infinity minus 1 whole power n minus 1 by 4 power n into 2n minus 1. Am I correct in writing that series? substitute n is equal to 1, 2, 3, so on, you check. I can say I should take 4 power n minus 1 because 4 power 0 won't come. If I take n is equal to 1, 4 power 0, 1, n is equal to 2, 4 power 1 will come, and so on. 2n minus 1. So n is equal to 1, 1, n is equal to 2, 3, right? All of you agree? Now, here the two series, what I am taking it is 1 by 4 per n minus 1 is one series, nothing but the other one is 1 by 2n minus 1. Now, what about the plus or minus symbol there? Whether I need to consider or not. So here the question arises that since I require a convergent series and a monotonically decreasing series, I will take that this is my an. An is equal to 1 by 2n minus 1. It is always monotonically decreasing, I know. And for this part, since the series is alternative, I will take un is equal to minus 1 whole power n minus 1, 1 by 4 power n minus 1. So, to verify the convergence of un, I can apply Leibniz test, or straight away I will do mod un. So, if I take mod un, it is nothing but 1 by 4 whole power n minus 1. Since it is a geometric series with a common ratio less than 1, it is convergent. If I write sigma un, it is sigma 1 by 4 whole power n minus 1, which is convergent. Because summation r power n is convergent if mod r is less than 1. Because every geometric series with a common ratio less than 1 is convergent, which we know that. So there are two choices. In proving the convergence, you can apply Leibniz test or you can apply modulus. So why I have chosen this example means Abel's theorem will be applicable for the regular series as well as the alternating series. That's why I have chosen the two examples. One is the regular one, another one is the alternating one. So if you want to summarize, the whole idea of infinite series is nothing but testing the nature of convergence for a given series, not finding its limit. And earlier we have done the primary tests like limit comparison, comparison test, ratio test, root test. As and when these tests will fail, we go with the advanced tests like logarithmic test, Bertrand test, Gauss test, Rabi's test, Cauchy's integral test, etc., etc. And however, these tests are not mandatory to follow in a specific pattern. However, the pattern is useful, which we have drawn as a diagram for majority of the problems. We follow the same approach. And the last part is nothing but alternating series, in which terms are given as alternatively. The common test always we use is Leibniz test, and we follow that. And whenever, if you want to make the discussion on absolute convergence, we always start with the problem with mod un and we solve the problem. If it is absolutely convergent, then it is okay. Otherwise, we should go for conditional convergence also. That is the whole idea. And we can make use of this Abel's theorem as and when required as per the difficulty level of the problem. That's it. Uniform convergence, I want to treat it as a separate topic. Because unless you get a confidence over this infinite series, I don't want to start with uniform convergence. It takes two classes for you, the discussion on uniform convergence. So after taking limits and continuity and derivative part, I want to start with this. At the end, I just want to discuss. Because after giving an assignment to you, I will give the concept of uniform convergence. And let me know how many of you are started doing the textbooks or not yet, or any one of you have reviewed them. or at present you are taking notes of the class and later you are going to start on it? Please tell. About to start, one person. What about the others? Only class notes. That's good. Same here. Fine. Then mostly I wish to give a assignment on tomorrow. Then I think that it is better to give the test conditions there for you so that you can have an idea. So my intention is, can I sum up at least 50 to 60 questions for you as an assignment? Considering all the tests, at least you can take 1 week time to solve them on your own. So I just want to say that I will give the problem simultaneously. I will give the hint also what test condition you are going to apply there. I don't want to reveal the answer whether it is convergent or divergent. I will give the test condition only so that you can cross check with the answers with your friends. Is that useful to all? Fine, I will do like that. So thank you very much. That's all for today's session. And in the no, because if there are some freshers who are learning for the first time, they will lose interest if we didn't give the test condition. Then I will do like this. Whoever want to do the problem on their own, don't see the second page. I will give the hints on second page. I just give questions on first page. That will be somewhat different, so that it won't deviate the others. Yeah. So any feedback from you with regard to this session on infinite series? You need any improvisation at any part, or the concepts are well understood by you as per the explanation is concerned? Right?